Hello, welcome back to BlenderSushi live noding. In this video, I'm going to cover this super formula 2D. It's not a super formula like a car racing. This is a super formula like a math functions here. Actually, I was inspired by this video. It's about VEX in Houdini. Houdini is the big brother of 3D node-based program. It's a very powerful. It's from Side Effects. Um, I found this video by accident, and it was talking about VEX in Houdini, and it's dealing with super formula. And if you look at the video at the beginning, there's a nice kind of information on how to think about the super formula and how to get to that kind of result that you might see here. Over here you see the curve. That's the curve here is the result of the super formula. It's basically just a math functions, and in this video it's all, the guy also explained that you can use this formula up here, and just by simply using this and applying it to the theta of the like a circle of functions, it will deform the circle, so it's looking more or less like this kind of shape. It's similar to the flower kind of design, and also the formula is not that different to the phyllotaxis or the sunflower kind of formula. So what I'm gonna do is I already copy all these functions from Houdini VEX. Houdini VEX has its own kind of functions to create points, and I will use Sverchok to do this. You can also use animation nodes. It's just slightly different, but it's because both Sverchoks and animation nodes use Python, so we can use either add-ons to do this to create this super formula curve. We're gonna do the 2D one, and yeah, let's see, have a look. Let's open Blender. I have the version that I made earlier, so it's basically something like this, and the Sverchok formula looks something like this, and the node tree, because I made this kind of setup, so I end up with something that looks like a pole, and the actual super formula curve itself is just that this guy up here, this shape, and this is the script nodes that we're gonna kind of port it from Houdini VEX. So let's get started from scratch. Hide the lamp and the light, delete the default cube, files, save as. This is SV super formula demo 001. At the end of this video, I might just give you the formula for it, but I recommend you to kind of have a look at the Houdini VEX video, and also check out the formula for super formula at Wikipedia, and try to recreate it yourself. The most important here is not the formula itself, because the formula itself is like a smart someone, like a genius mathematicians already make the formula for you and for us, and then we can just use it. We've done this before, with a script node, and this is kind of similar. This is kind of like just a porting of math formula, so it's rather supposed to be simple anyway. But I will give you I'll show you the process, so you will learn something. We're gonna use the petal sign, or I actually like the spiral Fibonacci example, and let's load this, and then we can see the spiral Fibonacci script node, and it's looking something like this. So there is a Sverchok define function, blah blah blah. I will actually put this module loading function loading at the top and remove the indentations. So this is much cleaner, I think. Now let's separate. So the output is going to be just vertices, and we learned that before. If we check it in the view row, so it's looking. This is for the spiral Fibonacci, the pilot axis, sunflower kind of pattern. By default it says 1000. I'll reduce this to 200, and then the C is the scaling. I'll just change this to 0.1. Reload, clear, and reload. I'll rename this into Super Formula Demo. Clear, and let's just get that guy and then reload it. Okay, now all what we need to do is just to copy and paste the functions that's used in the Houdini VEX. Okay, Houdini VEX is more like it's a little bit like C programming. It's not like Python. With Python, you don't need to specify the integer or float. This is the actual super formula itself, and there is this polar to Cartesian conversions, blah blah blah, and then there's this Houdini VEX functions. So I'll just copy the whole thing. We can see there's actually the loop. What's important here is this guy that's actually inside the loop. I will copy this. That's the super formula functions, and I'll paste it here. I have to be really careful with the indentations. Let me quickly fix the indentation real quick. So there's this polar to Cartesian thing. That seems to be correct, and the rest of them is for Sverchok. Output is going to be the vertices and blah blah blah, and then the input we're gonna add more variables at the top. The vertices, this is gonna be the vertices list, so we need that, and this is the function, super formula function. We can see these functions that's generating the pilot axis sunflower kind of points here. We can actually reuse this and then get rid of the one from VEX functions. Yeah, let's do that first. Let's copy that. I will comment this out. So whatever commented with a hash will not be read by Sverchok. So for blah blah in range, so we can replace this line, and then there must be like okay, we don't need this add point because Sverchok will generate the points for us. There's a cos phi, sin phi. I think everything else is pretty much okay. We don't need the float stuff. Can get rid of it because Python will read it anyway. So pos x, pos y. This is gonna be like a variable that we can use. And then at the very end, we're gonna use this vertex append. Something like that. I think it should basically will work. This one, the cos theta times r is actually up here. So there is a similarity in the formula. You see the cos and the sine. So that's good. We can just replace this with pos x and pos y. pause X, be careful with the bracket, and pause Y. Radius cos phi, the Z itself is gonna be 0, phi step. Okay, this is wrong. In Python, it doesn't understand this slash slash. Slash slash, it's like a commenting marking for programming language like C, I think, and VEX as well. So this should be just hash. Python don't mind this semicolon. Is everything good? Let's reload. It's complaining about something. Name M is not defined. Blah blah blah. Okay, we need all these variables. Okay, the segments we don't need to worry because it's already inside Sverchok. So this is super formula functions. At the top here we need the variable. Just get rid of all this. This thing should be float. I guess I have to thanks for the Houdini VEX video. We actually can just grab this formula. This is actually the super formula. It has a lot of variables, and this is all the variables with all the numbers that's gonna goes in and create something magical. Here we have the pi. This is a number that's representing the pi. We can just use real pi, I guess. 2 times pi divided by the segments. The phi is actually the theta. This is the theta for the angle. Yeah, I think that's pretty much it. Let's give this a test real quick. Reload. Complaining float R, invalid syntax. Float R. Oh, okay. Float R. We don't need that kind of variable type thing. Reload. Segments not defined. Okay, segments with our setup, segment is actually called N. So just replace segments with N. Reload again, and now seems to be it's not complaining anymore, and we get this. So that's magic. Okay, we already have the super formula working for us. There is these numbers that we can use to generate the functions. I think the one we currently using is this one, 4.5 10 10. Although it looks slightly different, but we're gonna deal with that real soon. So that's the formula. The segment, can we control? Yeah, we can control the point numbers. And then the scale factor. The scale factor should be the radius, I think. So this radius should be just the C. Reload, and now oh, actually there's this variable that we need to be careful. Okay, I'll just say radius over there, and then we're gonna tell Sverchok, okay, the radius comes from this. And this value right here. Reload, and still not too happy. Aha, okay, I have a feeling that we don't use this radius, but we're gonna use a scale right here. So maybe there's something that's not quite right in the formula. Reload, scale invalid syntax. Okay, it should be like that. Reload, number of points, and then scale factor. Okay. Okay, now seems to be correct. There's this R 1.0 here, and yeah, I guess that's that should be okay. Let's try this value. Okay, 7, 10, 6, 6. 7, 10, 6, 6, and reload. Refresh, and there you go. That's we get that kind of shape. 7, 10, 6, 6 for this kind of shape. What would be better is, of course, to have this variable outside here on the node input, so we can kind of further see the result instantly instead of going to the function and reload it. So file, save as again. Okay, so we have all this. We need all these variables to be outside. We're gonna do that real quick. So in this, using this, just copy this and paste. Oops. Copy this and paste. 1, 2, 3, 4, 5, 6. And this is gonna be n scale A, B, M, N1, N2, and N3. This is just all like a variable names. It can be anything, I guess. So I'll name this A, B. I use capital for the actual label for these variables. N3 scale. This is gonna be A equal 1.0, B equal 1.0, M equal 7.0, and then N1. This is gonna be the default value. Okay, there you go. I think it should be working. Reload it. Okay, we get this result. It's a bit small, so I might change the scale to 5 and then reload. Maybe scale to 2, and yeah. And here actually the A, B stuff, we can assign our variables into it. Reload, clear, and reload. Let's have a look. Number of points, okay, number of points working correctly. Scale factor A and the B. So A and the B is interesting. They need to be the same numbers, and looks like the bigger the number, the smaller our curve become. It's pretty interesting. And there's the M. Okay, the M seems to be, you know, just like the flower petal, you can have more or less of this petal, and we have the N. The N is actually the M, and the N is N1 actually is more, it's like the flower petal functions. They have 10. This one's okay. If I have this like really small, interesting. The points itself, the points is fine, but sometimes I rather have like a kind of like a curve. So I use the UV connections normally, and just plug it like this with a cycle in the U. Yep, and then if I bake it, see, I get this nice curve. So the M, apparently the M can be just integer actually. And then we have the N. So this N control the kind of have more control over the pedal, and then that pedal and that pedal. So just we can think of it like, okay, the super formula is in this case is more like a flower petal formula. So I keep saying about the petal formula. It's another script node. If we just get it from here, this comes with Sverchok petal sign, and then if we load it and then get it, we can see I'll create another of this thing and then plug that in there. So this is the other formula that comes with Sverchok. Increase number of petal, and then just okay, that radius, and then amplitude, resolution of the petal, and then okay, profile, and then number of petal. They are very similar, I think, somewhat, which is quite interesting, I found, just for comparison. So I'm gonna save this again. I save a lot, but that's okay. Better save than regret. So yeah, we can try all these number. Some of them not so interesting, but this one, let's say 16.5.5, 16. That's interesting. 16.5.5 and 16, and we get something like, whoa, that is easily exploding if we give a number that's too small. Okay, yeah, so that's interesting. I guess I will settle with one of them, like 6178. 6178. Yeah, that's pretty much like the flower petal. 73417. 73417. Slightly off kind of flower. It's pretty interesting. Yeah, let's play around with this a bit. There's a scale factor 73417. Interesting looking shape. As a bonus, I will show you like a little bit of kind of the magic of Sverchok. Is you see that this is like a two-dimensional curve, right? We know that if we have a bunch of curve, if you have like if you think of like a cylinder is made up of bunch of circle, and then it's being lofted. Now the thing about Sverchok is that we can use that kind of idea and we can assign a cylinder into this guy. What I mean is, if I use the matrix apply and matrix in, so I'm like duplicating this this curve using something like line. So I can, by default, line is kind of cloning the curve on the x-axis. I don't want that. I want it in the z-axis. So I'll just quickly do that. So now I'm duplicating these flower shapes going up in the z-axis. So I have multiple of these objects. The next thing I want to do is I could replicate the edge, like how many times? 8 times, so I can get something like this, and we can easily loft it using the cylinder. Actually, if I use a cylinder and then, okay, cylinders, how many, turn off the caps, how many subdivision do we need? Maybe 6, or I don't know, maybe same number as this. Let's check. The output polygon of this guy can be used for this, actually, for this lofted, for the the copy of this curve. Let's get rid of this GP layer for now. I think I forgot something. Oh yeah, I need to list join this guy, and by doing that, I believe we have the data for our cylinder, I think. The number of vertices is wrong. Currently, how many? Okay, 100 points. Let's try 100 points here. Okay, there you go. There you go. That's kind of result I was expecting. So this should be 8, 9, 10. Oh, 6 actually. 6 actually the correct number. We have this kind of problem, but we can use turn on these n-gon tessellations. Now we have correct looking cylinder, but this cylinder is made up of the curve of super formula. If I bake it, we get this, and check in edit mode. Seems like it's pretty good structure. Yeah, so this is the magic of Sverchok. Basically, we are using the polygon indices, polygon informations from this cylinder with a cap on or off, and the data for the curve itself coming from this super formula. And in order to make this correctly procedural, I need to make sure, okay, this integer, we need an integer for this line. So maybe if we have 8 here, we need we have to use math here, and then subdivide, minus subdivide it by 2, and it's gonna be the subdivisions. Okay, that's good. And the number of vertices, also an integer, should match this guy. there you go. Super formula, which is this guy. I will probably save this super formula somewhere. So we have super formula, and then we have this cylinder setup. We have control over the resolution, the vertices. We can add caps. Everything works properly. And then we can, of course, randomize, like we can randomize the scale, for example, to make this more interesting. The scale of each super formula. I'll show it to you. If we use range float, plug in as the scale, like that. Maybe I start from 3 and with 1, and then yeah, so I start with a scale of 5 maybe, and stop in scale of 0.2. The count I can control. The count actually should match the number of curve being copied. So count, start, stop, and there's a step. Start at 5, start, step, minus. So that's if we are using range float, but we could also use some things like math sign. Plug the number, frame number. Plug this into the sign, and plug this into this. Actually, use a map range. Alt min, alt max, the sign between -1 and 1, and new min, new max between 0.2 and maybe 5. So we have something like that. And I believe this, oh, okay, that's changing every frame. Maybe I overcomplicate things a little bit here. That's a breathing super formula. Let's see, I think 5 to 13, 13 should be good. 5 to 13, 13. It's like a flower petal, and we can have more or less. But of course, we have control over the N, N2 and N3. So that's the interesting part about this. I guess we don't need this scaling thing. Just keep it simple. So there you go. That's actually a 2D formula. There is also a way to make this a 3D super formula. This is the 2D super formula being ported from the Houdini VEX code. That's thanks to that other tutorial video. Yeah, I guess this should be interesting for you to try. I might post this script on the GitHub. Anyway, thanks again for tuning in to the BlenderSushi channel. Thanks for watching this video. I'll see you in the next video. Thank you.